physics, mechanics, and as you can see, we're actually getting quite close to the end of mechanics now. We are now not too far away from the end. We're at power and efficiency. Click. Okay. I think these are words you already know. Power, probably know. Does anybody know this word efficiency? Yeah, what would it mean? Simple meaning.
How do the machine work?
Yeah. Good in what sense though?
How much work it can do?
Yeah. Nearly.
Yeah.
How much
3%.
As a percentage, yeah. Yeah, so it is a percentage term anyways. Okay, did you write this down? Power and efficiency. Huh? Jerry, I thought you turned this on. Wait. There we go. I don't know. Could be. You don't think it's right? Google will tell me. EFFICIENCY. That is correct, believe it or not. Yes. Okay, got that? Power and efficiency. Yeah. Okay, now. So imagine you carried 1 kilogram up a hill, and now imagine 1,000 ants, little insects, each carry up 1 gram. So one at a time, each carrying up 1 gram, one by one. And on the top of the hill there are 2 piles, your kilogram and the ant's kilogram. So who did more work?
Same.
It's the same actually, because both did the same job, but there's something different about the ants. They took longer to do it. Yeah. So this means we need a new idea. It's not just work that we care about, we also care about time to do the work. So this gives us the idea of, and we can calculate it, so I won't bother. Power. So power is the idea of how quickly the work is done. So the definition of power is the rate of change of work done per unit time. So as a formula, what would it be? Yeah. So as a formula, it'd be work over time. And what would the unit be from this form? Yeah, watts, or joules per second. The unit is joules per second, but we also call this 1 watt. So the other definition you need for this slide is that 1 watt of power is 1 joule of work done in 1 second. Can you see okay? Yes? Yeah. Okay. We'll just wait a minute. Yes? Yes? Question?
No.
No? Okay. Bruce? Okay. Yeah, you have it, yep. Brian? Are you sure? Last word? Second. Yep, okay. So, we have these two new terms, power, which is work per time, and watts, which are joules per second. When you convert electrical energy into light energy, you've not used any energy. You know this from the last class. You've just converted it. But the electrical energy was converted into light, which you want, and heat, which you don't want. So, in fact, if you have a 100 watt light bulb, that means 100 joules per second. How much of it do you think is actually light and how much becomes heat? So 100 joules a second, how many joules will be light and how many joules will be heat? What do you think the ratio, the percentage would be? So you're saying 90%, 90 joules is? For the light, okay. You're saying 40 for light? Light, yeah. What are you saying? You're saying 40 as well for the light, 60 for heat. Anyone else? This is what you all feel about? Yeah, you're all wrong. Quite wrong, actually. The answer is 1. 1 joule becomes light and 99 joules become heat. Yeah, true. So, light bulbs, we say, are not efficient. They waste a lot of energy, an awful lot. So not 50-50. In fact, it's 1 and 99. So this gives us the idea of efficiency, how well the energy is converted. So this is now a new definition. Efficiency is how much useful energy you get out compared to the input as a percentage. So as the formula, it's useful output energy over total input energy times 100%.
Can I call it that letter?
Yeah, anybody know the name of that letter? The name of the letter? Not N. Yes, Jerry? I think you're right. Go ahead. What is it? No. I thought you said it. I guess not. Anyone know? Nope. No. Eta. ETA. Yeah. Well, here is eta. You know your Greek letters? Yes. Alpha, beta, gamma, delta. You know these?
Yeah, but I never heard it.
Ah, okay. Eta. Okay. Now, ideally you want 100%, but because of heat loss, it's always less than 100%. Interestingly, if we divide the top and the bottom by T, we get another useful result. So you have here efficiency equals the energy out over the energy or the work in multiplied by 100. If we divide by time, then what do we actually get now? A power. It doesn't really matter which we use. So if you divide by T, we can make it nearly the same thing. So it doesn't matter if you use energy or power for calculating, it's the same answer. So I think that's worth noting. You can do this using power as well. Okay, you have this? Yes? Okay. Bruce? Oh, that's okay. Efficiency is something you might have studied before in physics. Why is it impossible to have more than 100%? Yeah, you can't get more out than what you put in. In fact, even 100% is impossible. Has to be less than 100% always. Yeah. Okay. Got this, Brian? Bruce? I can wait, there's no problem. Sure. No pumpkin latte this morning?
After this.
Then pumpkin latte.
No, I don't like
No pumpkin latte?
not pumpkin latte at all.
Frappuccino?
They don't sell the pumpkin latte.
You have the picture for it.
Oh, really?
Yeah. You don't like it?
Yeah.
Delicious.
No.
You sure? Okay. Got that? Yep. Okay. Let's see. A boy lifts a 2 kilogram physics book off the ground, a height of 1.1 meter. It takes him 2 seconds to do this. What is the power in his arms? And he got his energy from his breakfast. However, half is wasted. Should be wasted as heat. What is his power now? Okay, so the first one is what's the power? So we'll do this one together. So this is 2 kilograms, and he lifts this 1.1 meters. Yeah. So the power is the work done over the time, and the work he's doing is given the book potential energy. He's putting this energy into the book. So that will be 9.81, 1.1 over 2. What's that about, please? Is it like 10 something?
10.8.
Okay. Now, is that input or output? In or out? Yeah. It's output because that's the work that you see done. That's what comes out of him. So the next part is, what is the input? And we're told that the efficiency is 50%. Half of it is wasted as heat. So we have 50% equals 10.8 over x, times 100%. So that means x, which is the input, 20.6, isn't it? No? Yes. Yes, 20.6. Yes? Trust me. Oh, yeah, sorry. 21.6. Trust me. Hmm? Mm-hmm. Got this? Yeah. Okay. Let's continue then. Got this, Bruce? Yeah, Brian? Yeah, okay. Okay, so we have a 1200 kilogram car, 1200, starts at rest and reaches a speed of 100 kilometers per hour over 10 seconds. If the car was 100% efficient, then what is the power of the engine? Okay, I'll give you a minute to calculate this because I think you can do it. So what is the efficiency if it was, what is the power if it was 100% efficient? Okay. Got that? Yes? So, no, not yet. Got both? Monica, nearly finished? Yep. Okay. Let me do another one here. Yeah, I think I'll do this one. It's interesting. Can I look at the answers for this now? Yep. Okay, so the first one, the efficiency is the output over the input. So what was the output here? It was given the car kinetic energy. So that's a half mv squared, and the input, did I tell you what it was? Oh, sorry, I'm doing this wrong. I'm not looking for efficiency, I'm looking for power, sorry. So power is a half mv squared over the time, which is a half 1200 100,000 over 3,600 squared over 10. So what is that then? 46303. Yeah. 46.3 kilowatts. Can I do another one here? The next part? So in the next part, it's 40% efficient. So now we have efficiency equals 40% equals. Now, which do we know, the top or the bottom, the input or the output? In other words, what is this?
The output.
Very good, the output. And the input is here. So the x should be 100, 10 over 4, 5 over 2, 20 something. 2.5? No.
Oh,
What's the x here? 5 over 2. 460, 230, 115. Is it 115?
115.
Kilo.
Yes.
Yeah. Okay, let's do a couple more. Let's find a hard one. Okay, I'll draw this picture for you. You can try it. So, here you have some oil. And here you have a pump. And the pump pumps the oil up to the top here. Maybe from like a, from a tank or something. And here's the information. I tell you that the pump is, let's say, 70% efficient. The oil comes out at 4 kilograms per second. this distance here is 10 meters, and the oil flows out here at a speed of 3 meters per second. Great, okay, this is all the info, and my question here is, what is the power of the pump? And just to give you a little hint, you can assume the oil here is at rest, of course. Okay, give this one a try now, see what you can come up with. Okay, any answers yet? Okay. Close. Actually, it could be that. I thought it was going to be a tiny bit bigger. It is in the 500s, though, is what I got here.
500.
No, it is in the 500s, so you're in the right area, but I think you're a tiny bit far away from what Oh no, wait, I apologise, this answer is a little bit different. It could be that, let's calculate it. So, here we have efficiency equals the output power over the input power times 100%. Fair enough? What's the efficiency here? 70%. The input power is what we're looking for. So the question is, what is the output power here? What is the pump doing per second? Per second it's taking 200 kilograms of oil, and what is it doing? It's raising it. So, and yes?
And give the speed.
And give the speed. Was it 4 kilograms?
Yeah.
I'm sorry, I thought it was, what am I thinking about 200 for? Oh, okay. Right, 4 kilograms, thank you. So, if I rewrite this, I get x equals 100 over 70 times 4, 9.81, 10 plus 2. What's the speed?
3.
The 2 was a half 4. What was the speed? 3 squared. And Lee, is this what you did?
No, I didn't do the kind of thing.
That's what you did. And what did you get here?
You made a for F.
Yeah.
Where does that be part?
The final answer, basically.
That's 10.4 and times 100 over 70 is 7.7.
5, 7. What did you get? 586.2. Okay.
I did
587 then, kilo. No, not kilo, just watts. Yeah? 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 Okay, I'll give you one more. A hard one now.
Oh. No, I mean, I timed that everything correctly, but when I timed 100 over 70, I put 40.4, not 10.4. I typed that 10.4, and then here I put 40.
No copy is the problem.
Yeah.
Yeah.
I will do the copy.
Okay, can I scroll down? Yes? Okay. Let's see, I'll give you another one now. One with a car. Okay, let's make its mass 1500 kg. Okay, let's give it a speed. The car has a. You know what? Let's look at a real car. Jeremy, what's your favorite car? Okay, let's make it a real car that we could buy. Huh? Bentley?
No, Benz.
What the heck is that?
B-E-N-Z.
Oh, Benz. Yeah, Bentley. Yeah. Mercedes-Benz. Which one?
I like the SUV, so.
Oh my goodness, it's going to have a huge mass.
Really, 250. Yeah.
Let's see. Mercedes-Benz.
GLA.
GLC.
No, I want GLA.
GLA.
Yeah,
Okay,
I
fine.
like
Fine.
better.
GLA.
That's one too.
Uh,
Wow. Maybe that would.
How much?
I'm looking.
That's
Do anything.
30,000.
No, we're making it real physics. Okay, 2017 Mercedes-Benz GLA 250. That's
Yeah.
nice.
Oh.
Okay. Let's see, what's its weight? Hang on, it doesn't tell me its weight. It's probably like 1,000,000 kilograms. Weight. I'm finding it. Give me a second. Specifications. Here's the weight in American pounds in kg. 1,495. It's not as bad as I thought. SUV. 1,495 kilograms. This car has a top speed of I'll tell you right now. Top speed in miles per hour, so let me put that in kilometers.
In highway is 7.61 over 100 kilometers.
Well, this one here is, the one I'm looking at is 214 kilometers per hour. Nice. Nice. And how long does it doesn't say how long it takes to reach this top speed, but from looking at the acceleration, it takes 6 seconds to get to about half of it. So I'm going to say it has this top speed and takes, let's say, 13 seconds to reach it. Okay? What is the power rating of the engine? And because I'm talking about, where's it gone? Top speed. What's another name for top speed? The name for it. Terminal velocity. So in this question we have to consider both this and this. Yeah. That's the reaction I wanted. So, I'll give you a minute to try it. This is quite a difficult one, but see what you can come up with. Sorry, KJ, do you have a spare pen?
No.
You have exactly one pen?
Yeah.
No, that's okay. Who has a spare pen I can borrow for just a minute? No, that's your pen.
No,
Is it spare?
I had.
KJ has one. He came to school with 2, thank you. Okay, making any progress? Right, let's have a look at this. Hard one. Yeah. First things first. Let's write down the UVATS. So the U is 0. The V is, what's it, 212 kilometers? So 214,000 over 3,600. 59 point. Okay. A we don't know. T is 13. S we don't know. Yeah. Okay. So what is the A here? I'm sure you got that. 4.57 meters per second squared. So what's happening is the car has a drag and a force here driving it, which I'll call T. And F will be T minus, well, yeah. What's going to happen is, we did this recently, at the very beginning, what's the drag? 0 newtons. But then at the very end, yeah, the drag is equal to the thrust. So when this is small at the start, then the force here is 0 newtons. 0 newtons. It's quite small. But as the car gets faster and reaches its top speed, then these two become equal. So if I look at the picture, we have a T this way, and this way we have on average, a half T. Are you worked out the T? Wonderful. So, what is the F here? T minus a half T, which is a half T, which is MA. So you get T is equal to 2MA. Do we know M? Yes. Do we know A? Yes. We multiply by 2. Is this what you got? Yeah. Yes. So what's T? Okie dokie. Thirteen, 6, 7. Okay, newtons. Great. But now what? We still don't have the power. So what's the formula for power? Oh, very good. Power is work over time, which is force times distance over time. But what's distance over time? Yeah. Now, it's not quite this. Average. Yeah, average. But it's roughly this. Roughly. But as you put it, this is average. Well, what's average? Average is U plus V over 2, which is in this case FV over 2, which is 13672 multiplied by 59.44 over 2. So what's that finally? 406 kilowatts. So 406 kilowatt engine. That actually sounds reasonable. Mercedes-Benz power of engine. I'm sure I can easily find that. .208 horsepower in watts. Okay. The problem is I had to guess this number. I think I guessed badly because the real answer is 155 kilowatts.
The time is too long.
You think the time is too long?
Yeah.
Yeah, I was thinking 4 was kind of puny. What would you, well, since you're the Mercedes-Benz expert, what would you put the time at?
5 or 6 seconds.
5 or 6 seconds?
I think like 45. Yes. Oh,
Yeah.
of course.
You know what, actually,
By driving.
because, from driving these, oh I see. Actually, because I know the answer, I could have put in the exact value of the time here. Let's see. 1, 3, 6, 7. Anyway, it's not a big deal because I just made up the numbers, but I think you're right. I think the time is too small. 13 seconds is quite too much power. You feel like this should have been maybe more like 40 seconds? I agree. I think 13 was too small. I think the time I don't think a car can reach its top speed in 13 seconds. I don't know. You think 25 seconds?
BMW is 25 to 300.
Oh, thank you. That's you should have told us this at the start. 25 seconds, you think, for BMW 0 to 300?
Yeah.
Okay. Good.
Economy is less short than the bigger.
Huh?
GLA is the smallest engine in BMW. 250, very small engine in
Yeah.
Mercedes.
Okay.
Because Mercedes always have 5 liter or 4 liter.
Yeah. Powerful engine. Yeah. Okay. Well, if we said, if we said 25 seconds, then that sounds a bit more reasonable then. Okay. Anyways, we don't need to change it, of course. It's just for practice. All right. We'll take a break for a couple of minutes before we start the next lesson then.
You break a lot.
Okay. Can I close this? No, not yet.
Even in reservoir question, what can be like MGH plus 2 half MV?
In the last worksheet,
Yeah.
I think I said in the question that the water comes out quite slowly, so we don't consider its speed so much.
Then shouldn't it be like
Even in the question that we did do with the oil, most of the energy was potential energy. I think it was something like, the kinetic part was like 2 and the potential part was like 100, It wasn't, I didn't feel you needed to consider it.
the V?
Yeah.
Then why do we put half MV there?
When? Today?
Yeah.
Because now I wanted you to consider it. I didn't want to make that question too difficult, KJ. That's kind of the main reason. Can I close this?